Okay, so we're going to continue taking a look at some of the more complicated ones. This is one that we kind of did in class, but not in this same format. We did this when we were actually going through and calculating up the cost of energy, electricity, from the electric company. But this is in a slightly different phrased way than what we looked at with the kilowatt hour. So this is one that you might have had some problems with. A particular type of automobile storage battery, well, that's a fancy term for we've got a car battery, is what we've got. That's basically what they're saying. We have a positive terminal and a negative terminal, much like a regular battery that we've talked about in class. It is characterized as something called a 236 ampere hour. Writing it out, I might call this, sorry about the dash, 236 amp hour, or ampere hour in its more proper term, but an amp hour. This is actually a common way to refer to things, although often for many batteries, especially the smaller, like the AA's, for instance, they're actually kept track of in something called milliamp hour, because they don't supply nearly as much current as a car battery does. Car batteries are actually kind of big when it comes to that. Let me see if I've got it marked on any of these. I will try and find that out and provide it to you. I know it shows up on some of the materials we look at. Anyway, 236 amp hour. And it has a potential difference, delta V, of, my numbers are saying 17.7 volts, which is not a bad value for a real car battery. Some have different potential differences, different voltages, if you will. The regular thing that I usually quote is about 12 volts for a car battery, but there are plenty that actually have a bit more for various reasons. All right. What total energy can the battery deliver? In short, they're asking how much energy is stored in the battery that it can actually release out. So here's the thing. In class, we talked about power being equal to energy divided by time. If I want to find the energy, I would multiply both sides by time. Here's where some of the stuff that we've done in class comes back into play. And I know that it can be frustrating because I don't necessarily always give you exactly robotically how to solve these problems. But what I want you all to start internalizing is relationships. Power is energy over time. They're asking us about how much energy we've got. Okay, so let's look at the one thing that we've used to find energy for. If you check back to your notes, when we were calculating up how much the electric company would charge you for the energy that you take from the electric company, you will find exactly this equation there, that the energy is going to be equal to the power times the time. All right, let's see. So that's helping us out some, but I'm going to need to do a little bit more. Power times time. Well, I don't know how long this battery runs is the problem. Let's talk about this unit, amp hour or milliamp hour. What this is basically doing, it's the same thing as the kilowatt hour. We can look at this in one of, well, not just two ways, but there are two ways that I could talk about it. We could be saying that it supplies 236 amp for 1 hour. This is an amp times an hour. In one of the other videos and other things we talked about, an amp is a coulomb per second. So if I take coulomb per time, charge per time, and I multiply it by time, I'll end up with a charge. Amp hour is like kilowatt hour. Kilowatt hour is a unit of energy, and amp hour is a weird unit of charge. This isn't in coulomb, because that would be amp times second. We could find how many coulombs it is, but that's not really what we're looking for right now. We'll see how to use this. But what this means is, when you see this battery, if we could, it probably won't, but it could supply 236 amps for 1 hour. That's a large amount of energy, it turns out, or I should say charge. We're going to find that it's associated with a large amount of energy. You could also look at this, that it could supply 1 amp for 236 hours, which is probably more likely a representation of what it is. You could also look at this as 2 amps for 118 hours, or 3 amps, and whatever this number is divided by 3, and so forth and so on. That's what this number basically means. When we talked in class about the difference between AA's and AAA's and C and D, we found that they all had the same potential difference. And we asked the question, why do you have different batteries? They have different amounts of charge that are stored in them. You'll find that they have different milliamp hours. Not amp hour, because they don't supply that much charge. They don't have that much built up into them. Turns out car batteries can be frightening things. Do not play around with car batteries unless you know what you're doing. Now that we've got that, we can understand that we could treat this as 236 amps for 1 hour or 1 amp for 236 hours. It doesn't make much of a difference because when we come down here, we can find that the energy is going to be equal to the power. Well, power is equal to I times delta V, or delta V times I. So if I use P equals I delta V, which is what we used in class, I can replace P with I times delta V. I wrote it backwards, but order doesn't actually matter here in multiplication. Well, delta V is 17.7 volts. My current, we don't know exactly what it is, but if we said that it pulled 1 amp, for instance, I could put in 1 amp, and it would do that for a total time period of 236 hours. I'm instinctively writing hours HR. Most of the stuff that I see is just writing them as H. I apologize. Part of that's because of Planck's constant, which we don't actually deal with, but it's something that I'm used to working with. You could also instead say, oh, but it's not drawing 1 amp. It's drawing 236 amp, but it would only do that for 1 hour. So this would be 236 amp, but only 1 hour. It doesn't matter when you multiply these together, you still end up with that same value. You could do 2 amp and be 118 hours, and it doesn't matter because when you multiply them together, they're actually going to come up to be the same thing. This is how you can make use of things that you see on a regular basis. You can actually Google right now the capacity of your cell phone battery. It will give you a result in probably milliamp hour. You can actually find out how much charge is stored in your battery and how much energy is stored in there as well. All right, let's finish this up. The energy is going to be nothing more than the potential difference times the current times the time that it can supply that current. And so when I look at this, I end up with 17.7 times 1 times 236. And I end up with, multiplying all of these out, I'm going to end up with a weird result. We'll deal with that in just a moment, but I end up with 4,177.2 volt times amp times hour. That's a little weird. Volt, amp, hour. What I actually want is an answer in joules. I'm not certain that they've specifically laid that out, but this is not a unit that people really work in. So what I need to do is I need to get the hour down into seconds. So here's what I'm going to do. I'm going to multiply this and convert the hours. 1 hour is 3,600 seconds. And this is going to get the hours to cancel out, and then I'm going to have seconds. You'll see how we can work with that in just a moment. My energy will be 4,177.2 times 3,600. We're going to end up with a big value, but as we talked about back in thermodynamics, a joule is actually a pretty small amount of energy. We've got 367. 1.504 times 10 to the 7th volt times amp times second. Let's work with that unit real quick. A volt is a joule per coulomb. This is a volt. Check your notes. We have that. An amp is a coulomb per second. This is an amp. And then we're multiplying by seconds. The seconds cancel out and the coulombs cancel out. And hey, look at that. We're actually left with a joule. They want the answer in joules, I believe. They may not have listed it directly, but when in doubt, always go with SI units. So energy, we should end up with 1.504 times 10 to the 7th joules, and that is exactly what I've got listed as the answer. This one's a little bit trickier, especially converting the hours and seconds at the end here. But to get them in regular units that we work with, that's what we'll end up needing to do. Now, on an exam, I might actually accept outright the volt amp hour if you actually have that set right. Or you could convert it into kilowatt hours, which is something that we've talked about before with our energy aspects. I could go through and I could actually work with that. However, right now I'm not particularly keen on it. A volt times an amp, well, actually, that's not that bad. Let's look at that. I'm slow. Might as well. It's 4,177.2. We said a volt times an amp times hour. And if you take a look at what we learned in class, a volt times an amp is actually a watt, because that's our power equation. So my energy would be equal to 4.1772 kilowatt hours. Kilo, because I divided it by 1,000. So, I apologize. We've actually got this in place. We could go farther than that, and if we use what we did in class, if every kilowatt hour costs 10 cents, it would cost you about 41 cents, maybe 42 cents to fully charge that car battery, in case you had to pull it out and charge it with a wall charger. All right. So those are other units that you might use. However, I don't think it's got it listed. In the answer key, they actually want it listed in joules, so please put it in joules.